Hello and welcome to this video on forces, in particular contact forces. So what are we going to look at? We're going to look at resultant forces and the effects of different forces on objects. Okay, so these are the objectives for today. Okay, so what are contact forces? Contact forces are forces that require things to touch. So pushes, pulls, thrust, upthrust, friction, air resistance, and something called the normal force. Non-contact forces would be gravity, magnetism, and the electrostatic force. So the ones you might not have heard of, the normal force, for example, is the force that stops two objects passing into each other. Upthrust is when a liquid pushes up on an object to stop it sinking. Okay, so we've got various objects here, and we're going to start with this book. What forces are acting on it? Well, first of all, we have gravity acting downwards. We draw the arrow downwards from the book and label that as gravity. Then there's the upward force from the table, which I've just talked about, which is what we call the normal force. Okay, because that force is the same size as the force of gravity, we give it the same size arrow. Next on this car, again, we have gravity. And we also have a normal force stopping it going down into the road. But we also have some horizontal forces on this car. That's what's enabling it to move. So we have thrust from the engine enabling it to move forwards. And as a result of its forward motion, we also get some resistive forces, which are going to be air resistance and friction. Okay, looking now at the boat. Again, we've got gravity acting downwards. And this time the force pushing it upwards, because it's in water, is what we call upthrust. Finally, we're going to take a look at the skydiver. And again, gravity acting downwards. And in this case, that's balanced by the upward force of air resistance, which is slowing him down. Okay, so we need to know what resultant forces are, and the resultant force is the sum of all the forces acting on an object. So in this first diagram, we see the upward and downward forces cancel out, the left and right forces cancel, so the overall resultant force is 0 newtons. In our second diagram, the up and down cancel again, but the right and left, if we take 20 minus 15, that gives us 5 newtons acting right. In C, we've only got two forces, they're equal size and opposite in direction, so again the resultant force is going to be 0. And in our last case, the up and down cancel again, and we're left with a 20 Newton force to the right. So what's going to happen to these objects? If they've got 0 resultant force acting on them, they stay the same place, or they stay travelling at a constant velocity, so their motion doesn't change. So this is what we mean if something is in equilibrium. If something is in equilibrium, there is going to be either it's not moving or it's moving at a constant speed. If your object is not in equilibrium, it will be accelerating, so getting faster. Or alternatively, it could be decelerating, getting slower. Or it could also be rotating. So, what factors affect the size of frictional and drag forces? The most important factor is going to be how fast something's moving. If something has a high speed, that means it's going to be rubbing up against more particles every second. It's going to be hitting against more air particles or rubbing up against more particles on a surface every second. So there's going to be a greater resistive force. Okay, the next factor that's going to affect the size of these forces is the type of surface. Okay, if there is a rough surface, then the result of that is going to be that there is more friction because the surfaces are going to rub together more. If it's a smooth surface, it's easier for them to move past each other. And we can add something called lubricant, for example, oil, which reduces the amount of friction between the two surfaces because it reduces the roughness. It fills up in the spaces between the rough surfaces. Okay, so forces can also change an object's form. They can cause stretching and compression, and in some materials the change is proportional to the force applied. So what does proportional mean? Okay, so if something is proportional, or if two things are proportional to each other, that means if one of those things is doubled, then the other one is also doubled. Okay, so if we were looking at a graph that showed proportionality, what we would see is a nice straight line that goes through 0, or the point we call the origin of the graph. So we need to be able to describe how materials behave as they are stretched or squashed. And we use the idea of deformation and elastic deformation or plastic deformation. So first up is elastic deformation, like you might find in a spring. With elastic deformation, the object returns to its original shape and size after the force is removed. In plastic deformation, the object retains its changed shape, so it does not go back to its original shape. Okay, so what happens to the length of a spring when the force on it changes? Well, the first thing we need to be talking about is the term extension. And the extension is the change in the length of the spring. And it's a useful term for us to use when we're describing the way that springs change under tension. So, the rule for springs is called Hooke's law. And Hooke's law tells us that the force applied to the spring creates an extension, and it says that the extension of that spring is directly proportional to the force that's been applied. So what I was saying earlier, if the force doubles, the amount of extension is going to double. But that doesn't keep on happening. Eventually with a spring, it's going to reach a point where it stops elastically deforming. It doesn't go back to its original shape, and we call that the elastic limit. And at that point, the two things stop being proportional. So we end up with a graph that looks like this. We've got force on the x-axis, extension on the y-axis, and we see that initially it's a straight line, but then after that elastic limit, it no longer follows a straight line relationship, and you can be adding more force and the way the extension changes will vary. And at that point, we've got permanent deformation in the spring. Thank you for watching.